In this video, we're solving a perfectly elastic collision in one dimension by transforming to the center of mass reference frame. So if you've never seen this trick before, the idea is that if we switch to a reference frame that's tracking along with the same velocity as the center of mass of these two objects, then we can exploit a theorem of mechanics that says the net momentum is zero in that reference frame, and it essentially makes the final velocities guessable. This is a huge advantage compared to our other method for this kind of problem, where we would just write down an equation for energy and an equation for momentum, but then we're stuck with this hideous nonlinear system of equations that we have to solve. Well, we can avoid all that complexity here by just shifting our perspective into a new reference frame. So to get things started, we need to find the velocity of the center of mass of this system. So I have one car with a mass of 1.2 kilograms moving to the right at 0.8 meters per second, and a second car of mass 1.5 kilograms moving to the left at 0.85 meters per second. And what we're going to use here to get the center of mass velocity is this fact from mechanics. So it turns out that the net momentum of a system is given by the total mass of that system times the velocity of the center of mass. And I'll post a link to where that theorem was first proved. So the way we use this is to solve for the center of mass velocity. So I need the net momentum of the system divided by the total mass. And the net momentum can be calculated by just looking at the momenta of the individual carts in the collision. So we have a 1.2 kilogram cart moving in the positive direction with 0.8 meters per second of speed. Then we have a 1.5 kilogram cart moving in the negative direction. So I just move the minus sign out in front there. And I have a 1.5 kilograms times its velocity of 0.85 meters per second. Then we divide by the total mass of all the different objects under consideration here. So that's 1.2 kilograms plus another 1.5, giving me 2.7 kilograms. And I'm going to keep a little extra precision on this answer. We arrive at a center of mass velocity that's actually leftward. So we're using a minus sign to indicate leftward. And it's actually a repeating decimal. It's 0.1166 repeating, but we're going to go ahead and round off at 4 significant digits as 0.1167 meters per second to the left. So now what we're going to do is transform into the center of mass reference frame, which means we want to take a fresh look at this collision, but imagine that we're running to the left at 0.1167 meters per second. Well, that means this car that's moving to the right is going to look like it's moving faster by 0.1167 meters per second. And the car that was initially moving to the left, now we're running to the left a little bit slower than that car, but the car is moving less than 0.85 meters per second with respect to this reference frame that moves to the left. So to transform these two velocities, and I'm going to use a prime for this to indicate that these are the velocities in the center of mass reference frame. Again, the car that was initially moving to the right, well, now we're running at it, so we're going to add in this center of mass velocity to it. So from the perspective of a person moving to the left at 0.1167 meters per second, that first car, the 1.2 kilogram one, is moving to the right at 0.9167 meters per second. Now we go ahead and do the same thing for the other car. This will be the initial velocity for car number 2 in the center of mass reference frame. So again, I indicate that with a prime. And this one should look like it's moving slower from the perspective of a reference frame that's moving to the left. So we can keep track of this by being very careful with our signs. We're going to call the initial velocity in the lab frame negative 0.85 meters per second. And I'm going to do exactly the same transformation to it. I'm going to add 0.1167, and that's going to give me still a leftward velocity, but it's going to be smaller in its magnitude. And this gives me negative 0.7333, again, just keeping 4 significant digits for the middle of our calculation. So that's what the initial state of this collision is going to look like from the perspective of a person moving to the left at 0.1167 meters per second. And the whole reason we did this is because there's a very special thing about the center of mass reference frame. Again, we go back to this theorem of mechanics. The net momentum is equal to the total mass times the center of mass velocity. Well, if I talk about this inside the center of mass reference frame, again, just indicating that with a prime, the center of mass velocity is 0 from within the center of mass reference frame because our origin is just tracking along with the center of mass. And that means the net momentum in the center of mass frame must be zero. And this zero is actually what makes our final state of the collision guessable. So let's look at a new graphic where we view the collision in the center of mass reference frame. So there's the results of our calculation. We have an initial velocity to the right of 0.9167 meters per second for the smaller car, initial velocity to the left of 0.7333 meters per second for the bigger car. And we know that both momentum and energy are going to be conserved in this collision. But we also know the net momentum is zero. So the initial and final net momentum in the center of mass frame, those are both zero. So all we have to do at this point is simply guess what the final velocities are in the center of mass frame to keep the momentum at a net value of zero, but also conserve energy. And the way you do this is with a simple guess. My final velocity for the 1.2 kilogram car is just the negative of its initial value. That means that car has the same energy it had in the initial state, but the momentum has the opposite sign. Final velocity for the second car is just the opposite direction, so it's going to be a positive 0.7333 meters per second. And again, that guarantees that car has the same exact amount of energy it did in the initial state. So energy is conserved by doing that, but momentum is also conserved because I'm still taking the exact same value here of mass times velocity for the first car and the second car, just with the opposite signs on them. So when I add them up, I still get zero net momentum. So that's the moment where we cut out half a page of algebra. We didn't have to solve a nonlinear system of equations to get these final velocities. We were able to simply guess the result because we viewed the problem from a really convenient reference frame. Now there's one thing left to do, and that's translate back to the lab frame. So this is what it looks like if we're running to the left at 0.1167 meters per second. What does it look like if we put on the brakes and we view it from a stationary reference frame? So remember, running to the left will tend to make a leftward pointing velocity look slower and a rightward pointing velocity look faster. So we're going to make sure that the increase in magnitude for the first one and decrease in magnitude for the second one work out when we do this frame transformation. So back to the lab frame here, I want to find V final for the first car, and that's going to be its velocity in the center of mass frame, which was negative 0.9167 meters per second. And now our transformation is minus 0.1167. That's going to make this car look faster than it looked in the center of mass frame. Remember, in the center of mass frame, we were running the same direction as that 1.2 kilogram car in the final state there. So when we put on the brakes, it's going to look like it's going faster to the left. And now we're going to round to our traditional 3 significant digits for the final answer. So we find a final velocity in the lab frame for the smaller car of negative 1.03 meters per second. Now for the second car, remember in the center of mass frame, that had a velocity of positive 0.7333 or rightward at 0.7333 meters per second. And in the center of mass frame, that one looked faster than it looks in the lab because we were running at it. But notice that the transformation just has the exact same sign. You're going to do the exact same transformation to each velocity. This time we do a minus 0.1167 instead of a plus. And as we expect, this car should be moving slower in the lab frame than what it looked like in the center of mass frame. And this gives us a final velocity of positive 0.617 meters per second. So I want to make a couple points before we wrap things up. First, there's just a pragmatic point here. Once you get the hang of switching into the center of mass frame and then switching back, you're saving a ton of work. So we just completely avoided all the algebra involved with solving a nonlinear system of equations where we would normally generate that by writing down an equation for momentum conservation and another equation for energy conservation. And then there's the philosophical point. I just wanted to mention that this is a wonderful prototype for the character of theoretical physics more broadly. So the more physics you study, the more you realize this is at the core of the philosophy of the subject. If you can find a new way to view a problem, even if it's a really difficult conceptual shift, if you can find a new way to view a problem that renders all the mathematics trivial and just solve a problem in that abstract space, for us that was the center of mass frame, and then you just transform the solution back to the real world, that's considered a far superior approach to the problem compared to just brute force grinding through the mathematics. Finally, if you're a little bit skeptical that this is even the right solution because it seems like such an exotic approach to the problem, go ahead and just verify that the momentum and energy are conserved in the lab frame. Calculate the initial momentum and the final momentum, and they should agree with each other within a slight amount of rounding error. And then do the same thing for the kinetic energy, and you can verify that this answer is actually correct. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.